This video is about temperature and heat and how we can calculate the amount of heat transferred when we observe a temperature change in a system. So first let's nail down a couple of definitions. So temperature and heat are both words that kind of, have similar meanings perhaps, at least the way we use them sometimes in our daily lives. But temperature and heat are actually different from the way a scientist or a thermodynamicist would consider them. Temperature, roughly stated, is a way of measuring the degree of hotness or coolness of something. So that's associated with, when we walk into a hot room or a cold room, we can actually quantify how that room feels in terms of relative heat or relative coolness in terms of temperature. And so we use the thermometer to do that, and we measure that in some temperature scale like Celsius or Fahrenheit or Kelvin. Heat, on the other hand, we can think of that as energy in transit. It's a way of transferring energy. So heat is a way of transferring energy. And by transferring energy into or out of a system, it can change its temperature as part of that process. So heat then is a way of transferring energy. And a way of thinking about heat as a transfer of energy, I have a little analogy that I sometimes use. And the analogy is to money. So think of checks and credit cards as a way of transferring money. They are not money themselves, but they are a way of transferring money. In a similar way, heat is a way of transferring energy from one place to another. We sometimes say that heat is a form of energy, but really heat is a way of transferring energy. But because heat is a way of transferring energy, just like checks and credit cards have units of dollars, heat will have units of energy. And the unit of energy, the SI unit for energy, is the joule, given the symbol capital J. And so we will use that most often. There's an older unit that you will sometimes see called the calorie, abbreviated CAL, for calorie. And 1 calorie is equal to 4.184 joules, so there's a nice conversion factor between them. And a calorie was defined as the amount of heat energy that you have to put in to raise the temperature of 1 gram of water by 1 degree Celsius. You might be familiar with calories spelled with a capital C. The capital C calorie is the food calorie, and it's equal to 1 kilocalorie spelled with a lowercase c. So this food calorie is 1,000 of these thermochemical calories. And we could relate that to a certain number of joules if we wanted to. So that's the difference, the distinction between temperature and heat. Temperature is a measure of how hot or cold an object is. Heat is a way of transferring energy. And as we transfer energy into or out of a system, it might warm up or cool off. So let's make that a little bit more clear by looking at a particular kind of example. So imagine that I have a cold brick. So I'll draw that in blue. So here's a cold brick. And we're going to set that on top of a hot brick. So here's a hot brick. Okay, so what's going to happen? Well, we know what's going to happen. The cold brick is going to warm up, and the hot brick is actually going to cool off. So as time passes, what we will ultimately find is that both bricks come to the same temperature. We call that thermal equilibrium when that happens. And we can say that in this process, heat has been transferred from the hot brick to the cold brick. So we have transferred energy from the hot brick to the cold brick as heat. Now, sometimes people talk about heat flowing from one thing to another. It's better to talk about it being transferred. Back in the 19th century, folks used to actually think, scientists used to actually think that heat was a substance that they called caloric. And caloric was a physical thing that would be transferred from one object to another as it warmed up or cooled off. But now we know that's energy. And to think about how this transfer actually happens, we need to bring up our kinetic theory. So you might know the kinetic theory from thinking about the kinetic molecular theory of gases, and so this is going to be related. So let's imagine what's going on in the hot brick. So the hot brick is made up of molecules, so I'll draw those as spheres. And since it's hot, it has a high temperature, and that means it's going to have a high average kinetic energy. So I'll abbreviate kinetic energy KE, and AVG period is my abbreviation for average. So that has a high average kinetic energy. And you'll remember that kinetic energy is related to how fast atoms are moving. So it's related to the velocity squared, so how fast the particles are moving. So in this case, at the high temperature, we imagine that these particles are moving really, really fast. So what does it mean to be a solid and be moving really, really fast? Well, they can't move very far, but they can knock into each other really hard and really rapidly. So an analogy to this, imagine that you're in a subway car in Tokyo, Japan, during rush hour. And some of those train lines, they actually have people that service members that will help push you into the car. So those subway cars are actually packed really, really tight. Now imagine that you're going down at high speed down a really, really bumpy track. So what's going to happen? Well, you're going to be slamming against your neighbor really, really hard. You can't move very far, but you're going to be moving very fast and knocking against your neighbor back and forth. Well, that's what a high temperature brick is like. Now let's imagine that we bring in here a cold temperature brick. So here's our cold brick. And cold brick is also made out of atoms and molecules, so here's some of them. And since it's cold, we're going to imagine that they're moving really slowly. So what I'm going to do is draw really small arrows in here. So these are small arrows indicating that these molecules are moving really, really slowly. Okay, so those are supposed to be really small arrows. So down here I was drawing really big arrows. So these guys are moving really, really fast. So this is an analogy. Imagine that you're in a subway car and that subway car is stopped. So, you know, occasionally you'll shift your weight around and maybe knock up against another person, or they will knock into you. But there's not a lot of motion going on. So what happens when we bring the hot brick up next to the cold brick? Well, one of these hot brick atoms down here is going to slam in, boom, to one of these cold brick atoms. And what happens? Well, that atom's going to get a big kick, and it's going to get jostled into its neighbor, who's going to jostle into its neighbor, and so on. Similarly, at the same time, because there's a backwards push when this hot brick atom knocks into this atom, it's going to slow down. So it's going to begin slowing down. And so over time, what happens is these slow-moving molecules speed up, and the fast-moving molecules slow down until when we get to the end, everybody, all of the molecules, are vibrating at about the same temperature, about the same speed. So if we look at a set of these molecules, then they're both kind of knocking around here at kind of equal speeds. They're bumping into each other's neighbors at about equal speeds once we get to thermal equilibrium. So that's what we mean by a transfer of heat. We're actually transferring kinetic energy. That's one way that we could transfer kinetic energy. And the kinetic theory helps us think about that. So we transfer kinetic energy by having these collisions that cause other molecules that are colder to start accelerating, moving faster. And this idea that atoms, molecules, or ions are in constant random motion, and that the amount of motion is related to that their average kinetic energy is related to the temperature, is a very important idea in chemistry and really thinking about all of molecular science. So we will come back to this again and again and again as a very common molecular model that we've got things moving around in constant random motion. So now we want to come up with some way of measuring how much energy is transferred as the temperature changes. And to do that, we're going to introduce a concept called specific heat. But before I do that, I wanted to introduce a couple of important terms that we'll see in thermodynamics a lot. And that's the distinction between system and surroundings. So imagine that I take a beaker full of water and I set it on top of a hot brick. So in this case, I might be interested in studying what's going on inside this beaker of water. So in that case, the beaker of water is the part of the universe that I care to study, and I'm going to call that my system. So the system is just the part of the universe that's under study. The rest of the universe then is called the surroundings. And so that might include the hot brick or the beaker. And technically the surroundings really includes all of the rest of the universe that is not the system. But we really mostly are concerned with the immediate surroundings. So in this case, we know what's going to happen. We're going to again transfer heat. So we're going to transfer kinetic energy as heat from the hot brick into the system, the water, if the water is colder than the hot brick. And so in this case, we could say that the surroundings are losing heat and the system is gaining heat. So heat is being transferred from the surroundings into the system. Now, in between the system and the surroundings, so right, this thing that I'm drawing in purple, the interface between the system and the surroundings, we call that a boundary. And so a boundary will always separate the system from the surroundings. It might be a physical boundary like a wall or the side of a beaker, But it might also be an imaginary boundary, just a line that we draw in our imagination to separate some part of the universe from the rest of it. And some boundaries, physical boundaries, can have particular properties, like they might be insulating and prevent heat from going back and forth. They might be rigid so that they cannot move or expand, like the rubber of a balloon can. That would not be a rigid boundary. So those are some important terms that we will see in thermodynamics, and that will be important when we're talking a little bit about specific heat. So we'll be talking about the specific heat of a particular system, and we might be talking about the heat that goes into or out of the surroundings. So let's talk about specific heat by looking at a particular example. So this was an experiment that was performed by Joseph Black way back in the 1600s. So let's look at Joseph's experiment. So he took 2 samples of water of the same volume. So let's imagine 50 milliliters of water. And he took 50 milliliters of water at 100 degrees Fahrenheit. And Joseph Black also took 50 milliliters of water at 150 degrees Celsius. And he poured them together. So he got them at 100 milliliters, shake them up a little bit, and eventually they came to equilibrium at a temperature that was exactly halfway in between, so 125 degrees Fahrenheit. So then he did a different experiment using 50 mils of water and 50 mils of mercury, both at the same temperatures, 100 and 150, so he repeated the experiment. Then he poured those two together and shook them up so that they would come to thermal equilibrium. He ended up with 100 mils of total volume in his tube, in his beaker. The mercury, of course, heavier, settles to the bottom, and the water was on top. And it turns out they both ended up, both the water layer and the mercury layer, at a temperature of 115 degrees Fahrenheit. So what does that mean? Well, that's interesting. So the temperature wasn't exactly halfway in between, right? So if we think about it, the temperature of the water only went up a little bit, from 100 to 115, whereas the temperature of the mercury cooled down a lot, from 150 to 115. So Joseph Black was able to reason that the amount of heat that was lost by the mercury should have been equal to the amount of heat that was gained by the water. We call that the law of conservation of energy now. And if that's the case, then why did the temperature go down a lot for the mercury and up just a little bit for the water? Well, Joseph Black realized that water must have a different capacity for heat than mercury does. In modern terms, since we know that heat is a way of transferring energy, we might guess that water has many more ways of storing that energy than mercury does. And because of that, we can distribute that kinetic energy more places as potential energy, and so we can store it as potential energy, whereas we can't do that as much with mercury. So that would explain why water has, for example, a higher capacity for heat, using Black's term, than mercury does. Heat capacity then is the amount of energy required to produce a certain temperature change in a substance. So substances with high heat capacities, you have to put a lot of the energy in to get their temperature to change very much. Whereas substances with low heat capacities, you can put a little bit of energy in, a little bit of heat, and their temperature changes by a lot. So typically we discover that heat capacity depends on how much stuff you have. We say that it's an extensive property because it depends on how much stuff you have. It also depends on the identity of the substance. So if we think about Joseph Black's experiment, if we had done that similar experiment with, say, different amounts of water or mercury, we would have gotten a different temperature change, a different result. And also we've seen that it depends on the identity. So water's capacity for heat is different than mercury's capacity for heat. So we need to consider both of those things. Thinking about amount of substance again, it's real easy to see that if you put the same amount of heat into a test tube full of water or a swimming pool full of water, you will see that there are different temperature changes of those two substances. And we've already seen a good example of how the identity matters. So you put the same amount of heat into mercury or into water, you will get very different temperature changes. So in order to get one quantity that we could use that just depends on the identity, one thing that we could do is divide by a fixed amount of substance. So that gives rise to two kinds of heat capacities that we use. So one is called specific heat. Sometimes it's called specific heat capacity, and it's usually given the symbol S, or sometimes C with a little subscript S, or sometimes C with a little subscript SP. So you will see all of those notations for specific heat. Actually, I prefer CS, so I'm going to use CS. So specific heat then is defined as the amount of heat Remember, heat is a way of transferring energy, so we're talking about the amount of energy that we have to transfer as heat to raise the temperature of 1 gram of substance by 1 degree Kelvin. And since the Kelvin scale and the Celsius scale have exactly the same degree size, that's also the same as 1 degree Celsius. So if you heat something up by 1 degree Kelvin, you also raise its Celsius temperature by exactly 1 degree because they have the same degree sizes. Specific heat capacities then will have units of joules, so that's the amount of heat, per gram, because we're dividing by the number of grams that we have, and also we're dividing by the temperature in kelvins, or because the Kelvin degree size and the joule degree the Celsius degree size are the same, this can be joules per gram per degree Celsius as well. So either of those two units are exactly equivalent. Another way that we can define the heat capacity of a material is using a quantity called the molar heat capacity. And you'll sometimes see that as C with a little subscript M, or sometimes C with an overbar. And it turns out it matters how you measure these heat capacities, both specific heat and molar heat capacity. And so sometimes you will see a CP, subscript P, or subscript V to indicate that the heat capacity was measured under conditions of constant pressure or constant volume. So typically we do experiments in the lab open to atmospheric pressure, and so they're typically done under constant pressure conditions. So most heat capacities that you hear about, specific heats, are constant pressure specific heats or constant pressure molar heat capacities. So what's different about a molar heat capacity and a specific heat capacity? Well, a molar heat capacity, capital C sub M, is the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Kelvin or 1 degree Celsius. So that's going to have units of joules, so that's the amount of heat that we have to put in, per, in this case, mole, so we're dividing by moles, and then again by kelvins. Or, because the Kelvin degree and the Celsius degree are the same size, this can be joules per mole per degree Celsius. So either of those units are equivalent. And so that's what's different about molar heat capacity and specific heat capacity. So which one you use, which one you choose to use, will be determined by the units that you need. So if you're given a problem involving moles, you probably want to use the molar heat capacity. If you're given a problem using grams, you might want to use the specific heat capacity. And of course, you can convert between one and the other because you know how to convert between grams and moles. So let's look at some typical heat capacities. So here are some heat capacities for several different substances, and here in this column we have the specific heats, Cs, and here we have the molar heats, capital C sub M, so the molar heat capacities. So again, these represent similar kinds of quantities, but the only difference is we've converted between joules and moles. So for example, aluminum has a specific heat capacity of 0.901, its molar heat capacity would be 24.3. Water, liquid water, has a specific heat capacity of 4.18 joules per gram per degree Kelvin and a molar heat capacity of 75.3 joules per mole per degree Kelvin. Another thing you'll notice is that water has kind of a high specific heat capacity, high molar heat capacity, compared to many of the other substances that are on this list. That's one of water's very special properties and one of the reasons that it's very important to our planet. So water acts as a great source and sink for heat. So when it's cold, water is able to release a lot of its heat and help moderate the temperature. When it's very warm, water works to absorb a lot of that heat and store it to keep the temperature kind of cool. So that's why our planet in particular doesn't have very rapid temperature swings as we move from night to day like a planet like Mars might have, for example, where there's very little water. So how do we use these specific heat capacities? So we're going to scroll over here to this side and think about that. So we can use two important equations. So first, we're going to relate heat to a temperature change. So if an object changes its temperature, one way that it can change its temperature is because it has lost heat or gained heat. Lost energy as heat or gained energy as heat. So we want to relate those. So first we're going to define what we mean by temperature change. So we're going to call that delta. Delta just means change. Delta T means change in temperature, and we're going to say that that is the final temperature minus the initial temperature. So that represents the amount of temperature changes. and that will be either in degrees Celsius, degrees Kelvin, or it could be in degrees Fahrenheit. So delta T measured in degrees Kelvin or degrees Celsius will be the same number because the Celsius and Kelvin degree are the same size. So if your delta T is 10 degrees Celsius, it is also a delta T of 10 degrees Kelvin. So you would not convert between those because we're looking at differences. So we're going to use that as our definition for change of temperature. Now we can use some important equations to relate the amount of heat, and that's usually given the symbol Q, Q for quantity of heat. So Q right here is our symbol for heat. So that's the heat that goes into or out of a system. And that can be equal to the number of moles times the molar heat capacity times delta T, or Q can be equal to the mass times the specific heat capacity times delta T. In the past, some of my students have called this bottom one the MCAT equation because it looks like it spells MCAT if you think of the delta looking a bit like an A. So either of these formulas can be used to calculate the amount of heat that is involved when there is a temperature change. So let's use that and do a quick calculation. So this question, we want to know how much heat in kilojoules is required to heat 1 gallon, which is the same as 3.785 liters, of water from 25 degrees Celsius up to its boiling point at 100 degrees Celsius. So we're going to use our equation Q, and then we need to figure out, do we use specific heat capacity or do we use molar heat capacity? Well, in this problem, we were given an amount, a volume of water, so we're going to somehow have to figure out how much water we have. So we need a couple of other pieces of information. We need to know the density of water. So the density of water is 1.00 grams per cubic centimeter, and a cubic centimeter is the same as a milliliter. And so that's the same as 1 kilogram per every 1 liter. So we can use this to figure out how many grams of water we have. And so knowing how many grams, we're going to want to know the specific heat capacity. And so the specific heat capacity of water, CS, is equal to 4.18 joules per gram per degree Kelvin or degree Celsius. And so we're going to use degrees Celsius here. We can interchange those units, remember, because the Celsius and Kelvin degree are the same size. So I'm going to use this equation, M times CS times delta T. So I just need to figure out all of those pieces. So first, let's figure out what mass is. All right, so I've got 3.785 liters, and so I can use a conversion factor to convert that into mass. So I've got 1 kilogram per every 1 liter. So my liter units will cancel out, and I'm going to go ahead and convert that into grams. So there are 1,000 grams in every 1 kilogram. So the kilogram unit will cancel out, and that equals 3,785 grams of water. So that's how much water we have. Now we can plug it into our equation for heat. So heat is equal to 3,785 grams of water, and then our heat capacity is 4.18 joules per gram per degree Celsius, so our gram unit will cancel out. And then we have our delta T is next. So T final is 100 degrees Celsius minus our initial temperature, 25 degrees Celsius. And so 100 minus 25 is 75. And then we just multiply all those numbers together, and we get a final value of 1.19 times 10 to the 6th joules. And if we convert that into kilojoules, we divide by 1,000. So that'll be 1.19 times 10 to the 3rd kilojoules of heat energy. So that's how much heat energy we have to put in to heat up water.